everyone, welcome to part 1 of chapter 9. Today's lecture is all about solutions. First, we're going to talk about what solutions are and the factors that impact solubility. We're going to discuss how intermolecular forces allow us to determine which things are soluble and which will be insoluble. And then we're going to talk about the concentrations of our different substances. We're going to talk about them in kind of general terms and then apply some math to it. So, lots to cover today. Let's get started. So first we need to start off with some definitions. So we're going to spend this entire chapter talking about solutions, so we need to get a few things straight. Our solute is the substance that is being dissolved. Our solvent is essentially the thing that's doing the dissolving. Okay, so like if we think about some salt water, right? Our salt water, the thing that's doing the dissolving, that would be our water. So our water here would be the solvent. And a lot of times our water is our solvent. So most of the time our solvent will be water. And then the substance being dissolved, if we were talking about salt water, then our solute would be the salt. Okay, so again, the solute is whatever's being dissolved, and the solvent is whatever is doing the dissolving. And usually that's the most abundant substance in the mixture. And then when those are together, we call it a solution. And a solution is a homogeneous mixture of one or more solutes and a solvent. So again, whatever's being dissolved is the solute. The thing doing the dissolving is the solvent, and together they make up the solution, okay? And our solution will always be a homogeneous mixture, which essentially means it'll look like water, right? Like if you think about salt water, you can't tell there's salt in there unless you taste it because it's a homogeneous mixture. And a lot of times that will be true for our solutions as well. Okay, let's give this a go. So soda is a mixture of sugar and water. Which substance is the solute? So which thing is the one being dissolved? So our answer is sugar. Sugar would be the substance that is being dissolved, so that's our solute. The water here would be our solvent, and the soda would be our solution because the soda is then mixed together. All right, let's try this next one. That says a solution is prepared by adding 25 milliliters of ethyl alcohol to 75 milliliters of water. Which substance is the solvent? Okay, so do you see how here, and you may not know, but ethyl alcohol is a liquid and water is a liquid as well. So both of these are liquids. So usually that brings us to ask, okay, well, how do we know which one is the solvent? Because a lot of times we'll think of the solvent as being the liquid and the solute as being the solid. But it doesn't always play out that way. If they're both the same phase of matter, like this, they're both liquids, then the one that's more abundant is going to be the solvent, okay? So here, water's our solvent, and our ethyl alcohol would be our solute. So here's some other examples of solutions. So like I said, a lot of times we think of it as, a solid being dissolved in a liquid like salt water. Right? Our solvent would be a liquid, our solute would be a solid, and then when they're together, we get a liquid. That's usually what we think of. But like I said on the last slide, right, they can all be liquids. The solvent can be a liquid, the solute can be a liquid, and they can, the solution would then be a liquid. We can also dissolve gases in liquids. Like if you think about your soda, right, and the example here would be like carbonated water, but you could think about a soda as well. Your soda has carbon dioxide that's dissolved in the liquid. So here, your gas would be a solute. That gas is dissolved in the liquid. And our solvent would be, your soda and whatever else. And together, they make the soda overall. Okay, another kind of weird example is air. Air is also a solution. And we don't really think of air as being a solution. We just kind of think of it as being air. But you have some components of your air are more abundant than others. Like the most abundant portion of our air is nitrogen. Okay, but we also have oxygen, carbon dioxide. So the ones that are in a smaller amount, like oxygen, would be our solute. and the one that's the most abundant would be our solvent. So here that would be nitrogen. So it can be a bunch of different phases of matter. You just need to figure out what's being dissolved, or, if they're in the same phase of matter, which thing is the most abundant. Again, the one that's most abundant will be the one doing the dissolving, which will make it our solvent. So the way that we describe how much can be dissolved is called solubility. Okay, and we'll get to apply some numbers to that in a little bit. But just talking on a general term, if something dissolves in something else, like how salt dissolves in water, that we say is soluble. So salt is soluble in water because it dissolves. Or like bromine is soluble in methylene chloride because it dissolves. Sugar is soluble in water because it dissolves. Right? If something doesn't dissolve, then it is called insoluble. So like this picture here on the left-hand side, that's oil being poured into water. As you see, the oil is not interacting with the water, and it actually forms a whole separate layer up here. It's kind of cool, and we'll talk about why it does that in a minute. But when something is insoluble, then that means it does not dissolve. So like sand is insoluble in water. It does not dissolve. So soluble means it dissolves, insoluble means it does not. Okay? The solubility depends on the intermolecular forces. So see, this class likes to tie all of our stuff together, right? We just learned about intermolecular forces a couple chapters ago, and now that's going to help us to better understand solubility. So our rule here is like dissolves like. Polar compounds will dissolve in polar substances. So if you have something polar, the way you make it dissolve is to add something polar. So like dissolves like. For example, methanol dissolves in water. So methanol looks like this. I'll draw out the Lewis structure. So there's methanol. So methanol has two different polar bonds. This one is a polar bond and this one is a polar bond. And do you see it can undergo hydrogen bonding because it's got that OH group? That makes it really polar. Okay, in this chapter, we're not going to distinguish between hydrogen bonding and dipole-dipole. We're going to see that this is polar, so it will dissolve in anything that's polar. Water is a very common solvent that we'll use because water is polar, right? We've talked a lot about the fact that water is polar, and water has hydrogen bonding as well. So since these are both polar compounds, our water can dissolve our methanol. Pretty cool. But again, it's because they're both polar. The reason for this is our partial negative and partial positive charges here attract the partial negative and partial positive charges on our methanol. So like the partial negative of, methanol would be attracted to the partial positive of water or vice versa, and that attraction is what allows those molecules to dissolve. So similarly, nonpolar compounds dissolve in nonpolar solvents. So carbon tetrachloride looks like this, and I'm not going to draw out hexane because it's a really large molecule. You'll have to trust me that it's nonpolar. But carbon tetrachloride looks like this. And even though carbon tetrachloride has polar bonds, because all of those dipoles are equal and opposite, that makes this entire molecule nonpolar. So carbon tetrachloride is nonpolar, and so is hexane. So carbon tetrachloride will dissolve in hexane because they are both nonpolar. So again, polar compounds dissolve in polar substances, nonpolar compounds dissolve in nonpolar substances. Okay, so that's why we say like dissolves like. Polar stuff dissolves in polar solvents, nonpolar stuff dissolves in nonpolar substances. What I want you to remember is that water is polar. So anytime you see water, I want you to think, oh, that's a polar solvent. That will dissolve polar compounds. And anytime you see hexane, I want you to think, oh, that's a nonpolar solvent. It will dissolve nonpolar compounds. Okay, these are the two I want you to know. I want you to know water is polar, which you should know already and should be able to deduce, and that hexane is nonpolar. Hexane is a really, really common nonpolar solvent that we use in organic chemistry, and every once in a while we'll use it in Chem 20 or other levels of chemistry as well. But I do want you to remember that hexane is a nonpolar solvent, so it will dissolve things that are nonpolar. So our other kind of piece that we'll investigate is ionic compounds. So ionic compounds are usually solids at room temperature. They have really strong intermolecular forces which are holding them in the solid phase. So for example, sodium chloride, right? Table salt. That's a really easy example, and that's what's being shown in this picture, which we'll talk about in a second. But sodium chloride is a metal and a nonmetal, therefore that's an ionic compound. And again, really strong intermolecular forces holding that in the solid phase. Okay, so but ionic compounds, if you think about putting an ionic compound in water, that ionic compound is actually going to end up splitting apart into its ions. Okay, and we're going to get to this more. Oops, my apologies. We will get to this more in a later chapter. But when we put an ionic compound in water, it's going to break into the ions that formed it. So sodium chloride will break into sodium and chlorine, and those are charged species, okay, because they've transferred the electrons. So ionic compounds, most ionic compounds dissolve in water because those positive and negative charges on these ions that are breaking into pieces are being attracted to the partial negatives and the partial positives that we see on water. Okay, so there's water. So water, again, like I said, has partial positives and partial negatives, and those partial charges are going to be attracted to the full positive and full negative charges on the sodium and the chlorine. So if you look at this picture here, the small ones are sodium and the big ones are chlorine. So the sodiums are kind of like a, I don't know, purplish grayish, and the chlorines are green. Do you see that like this group of water molecules, right? The water molecules kind of look like Mickey Mouse ears to me. But the water molecules, the red part is the oxygen and the white part is the hydrogen. So this is oxygen, like I said, this is hydrogen. And then that's another hydrogen there. So when we have something like sodium, which is positively charged right there, do you see that all of the water molecules have oriented themselves so that their partial negative oxygens are facing that positive charge? Similarly, if we look at, this group of water molecules, do you see that the chlorine in the middle that's negatively charged, right? That's negative, and the water molecules have oriented themselves so the partial positive hydrogens are the ones facing that negative charge. Okay, so the water molecules are actually pulling off pieces of our sodium chloride crystal and then surrounding it. And then this is called being hydrated. Okay, because the water is dissolving our salt. So again, looking at this group of molecules, right, this group of water, they pulled off this positive sodium piece, and all of the water molecules oriented themselves so the partial negative oxygen is facing that positively charged sodium. In this group of water molecules, they pulled off a negatively charged chlorine, and the water molecules oriented themselves so the partial positive hydrogens are facing that negatively charged chlorine. So again, we're seeing the whole opposites attract. So this is why ionic compounds dissolve in water. The ions that are being formed are attracted to the partial, positive and negative charges on the water. Alrighty, now it's time to get some practice. Go ahead and pause here and complete problems number 1 through 7 on the Chapter 9 lecture worksheet. Once you're done, come back and we'll keep going. Alrighty, so now we've talked about how to determine whether or not something dissolves. Now we are going to talk about the rate at which something dissolves. So chemists can be impatient, right? And a lot of times we're trying to increase the rate at which something dissolves so that we can kind of move on with the next portion of the experiment. There are 3 different ways we can increase this rate of solvation. The first one is to increase the temperature, right? If we increase the temperature, that means our motion of our molecules will increase. Remember, as we increase the temperature, we are giving our molecules more energy. If they have more energy, then they're going to move faster. And if they move faster, then they can bump into the solute molecules more quickly and are able to dissolve them. Okay? All of these methods that I'm going to talk about are simply going to increase the rate at which solvent molecules kind of bump into our solute molecules. And the reason I say bump into them is because when they bump into them, they're able to use those intermolecular forces to allow the solute to dissolve. So the more kind of collisions we can make, right, the more that we can have these solvent molecules bump into our solute molecules, the faster it will dissolve. So again, by increasing the temperature, we make those molecules move around faster, then they bump into the solute molecules more and dissolve it more quickly. The next one is to stir, right? I know it sounds silly, but if you stir something up, it dissolves more quickly, but for the same reason, right? If we stir it, then our solvent molecules can go bump into our solute molecules and allow them to dissolve. Okay, you'll notice, like, if you've ever tried to make Kool-Aid at home, right, from the packets, maybe that's kind of old school, but you buy these little packets and you add sugar, and you need to dissolve the sugar. And the way that you allow the sugar to dissolve in water is you stir it up. It would dissolve eventually just sitting there, but it'll dissolve a lot faster if you stir it. And then lastly, you can crush the solid into tiny pieces. Okay, so I like to think about this as if I was going to put some sugar in my tea. I lived in London for a little bit while I was studying there, and everybody has tea. And so, if you put a sugar cube in your tea, it's going to dissolve a lot more slowly than if you put some kind of granulated sugar, like our regular sugar you might use at home. If you put granulated sugar in your tea, it will dissolve more quickly than a sugar cube because it's in smaller pieces. We call that having a larger surface area when it's all kind of crushed up. And that larger surface area from crushing it up allows the solvent molecules to bump into it more. Otherwise, if it was just like a sugar cube, then our solvent molecules would have to kind of bump into the outside and slowly break that cube down. Okay, so our three ways that we can increase the rate at which a solid dissolves essentially is to heat it up, stir it up, crush it up. Those are your three ways. But again, all of them allow our solvent molecules and our solute molecules to bump into each other more quickly, which allows them to dissolve. So we can't just, kind of keep adding solids and expect it to dissolve. There's a limit to how much solid can dissolve in a given amount of liquid, or how much gas can dissolve in a given amount of liquid. When it reaches the limit, it forms what's called a saturated solution. The saturated solution contains the maximum amount of a solute that will dissolve in a specific amount of water at a given temperature. So let's say we had a saturated solution, and like I said, that's holding the maximum amount that can be dissolved in that solution. If you add more solute, then it's not going to dissolve. It'll just kind of fall to the bottom and sit there, and there's nothing you can do to make it dissolve more. You can't stir it up or crush it up, nothing. It's not going to dissolve more. Okay. The saturation concentration, though, depends on temperature. Remember on the last slide, I said one of the ways we can get it to dissolve more quickly is by heating it up. This also helps us to increase the solubility of something, which we'll see on a later slide. At higher temperatures, we can actually dissolve more solid than we can at lower temperatures. My example for this to you is if you've ever tried to make hummingbird food. So hummingbird food is a saturated solution of water and sugar, and you have to heat it on the stove. The reason for this is if you were to take that amount of sugar and just put it in water, then it's not going to dissolve because it would form a saturated solution. It's too much sugar for room temperature water. But if you heat that water up, you can actually dissolve more sugar than you can at room temperature. So anytime we talk about a solubility limit, it's at a specific temperature, and usually that will be at room temperature. When we talk about gases, we also have to specify the pressure for gases because that makes a difference. More on that in a little bit. So again, saturated solution contains the maximum amount of solid that can be dissolved. A solution that has less than the maximum amount is called an unsaturated solution. So if I added more solid, it'll just keep dissolving, right? Because it's not saturated yet. It's unsaturated. It can still dissolve more solid. And then a solution that has more dissolved solute than it should is called a supersaturated solution. Okay, and I want to be super clear. This is a very, very special condition. It's very unusual that you will see a supersaturated solution. I actually posted a video in Canvas showing a supersaturated solution, and it's really neat. So make sure to check it out. Also, you have an extra credit opportunity this semester, and that is to make a supersaturated solution, and you'll be making rock candy. So if you've never made rock candy before, this is your opportunity, and like I said, it's an extra credit assignment. There's more information on that in Canvas, so make sure to check it out and get experience at home doing some supersaturated solutions. But the other example that I was talking about earlier with the hummingbird food, so hummingbird food is actually a slightly supersaturated solution because you have to heat up the sugar in order to make it all dissolve, right? So once we heat up that solution, all of that sugar dissolves and you cool it down kind of slowly to make it stay in solution. But again, this is a special condition. It's kind of hard to do, which you'll see if you go make rock candy. It doesn't always work because it's tough, right? So I think you're going to have a lot of fun though. So if we have something that is unsaturated, if you add some more solute, then it's going to dissolve, okay, because it hasn't reached its solubility limit. If you have a saturated solution and you tried to add more solute, then it's not going to dissolve and it's just going to fall to the bottom and sit there, right? Because our liquid is saturated. It cannot dissolve any more of our stuff. If you have a supersaturated solution and you try to add more stuff, you actually kind of mess up what's going on in here, and it will form these crazy jagged crystals because supersaturated solutions are very unstable, okay? Supersaturated solutions, I like to say they're moody. If you even look at these things wrong, they're going to kind of freak out and form crystals because they're temporarily holding more solid than they should be. They're very unstable and they will just tend to kind of, we call it, in chemistry, we call it crashing out of solution. And they'll form, like I said, these kind of weird unstable crystals. To get them to stay in solution is actually pretty tricky. So if you do make rock candy, you will be making a supersaturated solution, and then you are going to make these crystals grow on a string over about a week, which is pretty cool. So pressure also affects our solubility if we are talking about a gas. Pressure does not affect the solubility of liquids or solids. So if we were thinking about, dissolving sodium chloride in water, the pressure does not affect it. But pressure does affect gas solubility, okay? And the pressure, or the gas solubility is proportional to the gas pressure over the liquid. What I mean by that is that the higher the pressure, the more dissolved gas you can have. Let's take, for example, a soda. And whenever you think about gas solubility, I always want you to think about, how would I want my soda? Okay, so if you're going to buy a soda, you would want one that's closed, right? You don't want one that's been open for a while for really obvious reasons, right? If it's been open for a while, it would be flat, right? All of the carbonation would be gone, and that kind of destroys the whole fun bit of drinking the soda. So what you want is you want it to be closed so that it's still under pressure, okay? You'll notice that when you open our soda, it'll go tss, and it's because we're releasing the pressure. Once you release the pressure, that dissolved carbon dioxide is able to leave the liquid. But once if you keep that cap on or you keep that lid sealed, then it's staying under pressure, and that pressure essentially forces that carbon dioxide into the liquid. So we want high pressure for high solubility. So that's why we say it's proportional. We will get a higher solubility of our gas if we have a higher pressure. If you release the pressure, then all of that gas can leave. Okay, so here's kind of our summary. The solubility of a gas increases with increasing pressure. More gas will dissolve at higher pressures. So let's look at temperature. So we've talked a little bit about temperature already, and I told you that for solids, our solubility increases with temperature, mostly. So our solids on this slide are our red lines. Do you see that for the most part, they're kind of increasing as they go from, left to right? They're pretty much all going up, with the exception of, lithium sulfate, which don't worry about that. I just want you to remember in general. So in general, our solubility increases for our solids at higher temperatures. And again, I want you to think about, okay, if we want something to dissolve, we're going to heat it up so that our solvent molecules have more opportunity to interact with our solute molecules and dissolve them. So for solids, we want a high temperature for good solubility. However, if you look at our gases, our two gases here are shown in blue. Their solubility decreases with temperature. So solids increase, gases decrease. And again, I want you to think about how you want your soda. Okay, so if we think about our soda, we wanted it sealed, right, so that it's under high pressure, and you also want it to be cold, right? At lower temperatures, our gas molecules are able to stay in the liquid better. Once we kind of heat up our gases, right, we heat up our soda, that gives our gas molecules more energy, and they're able to kind of break the intermolecular attractions that are keeping them in the liquid and leave. But if they're cold, then they don't have as much energy, and they're less likely to kind of leave our liquid. I mean, they will eventually, right? But they're less likely. So for gases, we want our soda sealed, and we want it cold, right? We want it under high pressure and low temperature. That is how gases dissolve the best. For solids, though, we want high temperature, so we get those liquid molecules bumping into our solid. So let's look a little bit more about solids in water, okay? So we will actually describe the solubility of solids in water usually by the grams of our solute that can dissolve in 100 milliliters of water. And usually it will be at some specific temperature. So if you look, we have temperature here on the bottom. So these are called solubility curves. And you will make a solubility curve for each individual substance, right? So all of these are solids. And again, most of them are increasing, going up to the right. So our solubility is technically defined as the amount of a substance that will dissolve in a specific amount of solvent, usually that's in 100 grams of water, at a given temperature. So let's look at this. This says how many grams of ammonia are needed to create a saturated solution at 30 degrees Celsius. Okay, so remember, each one of these substances, right, usually they're solids, but each one of these substances has their own solubility curve. So we need to find the one for ammonia. This is ammonia here. Ammonia is a gas, okay? So you'll notice that as we increase the temperature, its solubility is going down. So that makes sense, right? Because as we increase the temperature, we're giving those gas molecules more energy, and they're able to leave our liquid. So logically, that makes sense. So now let's look about the problem though. How many grams of ammonia are needed to create a saturated solution at 30 degrees Celsius? So these lines that you're seeing for each individual substance, those are representing the saturated point, right? So that's our saturated limit. Okay, so if we look at 30 degrees Celsius and we kind of go up to find our line for ammonia, that's right there, okay? Because this here, that's our ammonia line. So we want to figure out, okay, at 30 degrees Celsius, how much of our ammonia can we dissolve? So we would just go over here, figure out where that intersects. Looks about 41 grams. Okay, so if it's on the line, then that's telling us the amount that makes a saturated solution. Anything below the line would be unsaturated. Anything above the line would be a supersaturated solution. But again, like I told you, that's kind of a rare incidence. Let's try number 2. This says what temperature is needed to create a saturated solution of 70 grams of ammonium chloride. So again, we need to go find our line. Okay, so here's our ammonium chloride line. And we are going to make a saturated solution. So that means it's going to be on the line of 70 grams. So here's 70 grams. So we're going to go, okay, where does this intersect? There's 70 grams for our ammonium chloride line. Looks like 90 degrees. Okay. Our next one says a solution is prepared by adding 30 grams of sodium chloride to water at 80 degrees Celsius. Would this be unsaturated, saturated, or supersaturated? So we have 30 grams, so here's 30 grams, and 80 degrees Celsius. So if we go 30 grams at 80 degrees Celsius, that puts us right here. And we're talking about sodium chloride. So here's sodium chloride. This is our sodium chloride line. Do you see that that dot we drew is below the sodium chloride line? That tells us that this is unsaturated, right? Where we have less solid than the maximum amount. So that is unsaturated. Our last one says, how many grams of ammonium chloride are needed to make a saturated solution at 50 degrees Celsius? Okay, so we're doing ammonium chloride again, that's this one. And we have 50 degrees Celsius, we want to know how many grams. So you go 50 degrees Celsius up to the line, and we go over, and we find out that's about 50 grams. Okay, so again, hopefully these are pretty straightforward. Each individual substance has its own solubility curve, and we can use that solubility curve to tell us the maximum amount of that solid that can dissolve at a specific temperature. And then we can use that to figure out, okay, if we know this much dissolved at this temperature was at, unsaturated, saturated, or supersaturated. Pretty handy little curves. Okay, so we've talked about solubility, but now we need to talk about concentrations, because solutions can have what's called a variable composition. For example, if I was going to make some salt water at home, if I added just a pinch of salt to, say, a pot of water, that is probably going to be unsaturated, right? Because I could add more salt and it would keep dissolving. So just using general terms like unsaturated, saturated, or supersaturated doesn't tell us a lot about, okay, well, how much dissolved? Like if it's unsaturated, well, by how much, right? And so we need to have another way to describe these amounts. Okay, we have two terms. These are dilute and concentrated, which are going to be kind of relative terms. They are qualitative descriptions of the amount of solute in solution. Okay, dilute would be not a lot is dissolved, just like a little bit, right? Again, like a pinch of salt in our water. That would be dilute. Whereas concentrated would be a ton of salt in our water. Okay, so dilute, not very much solute. Concentrated would be a lot of solute. But again, these are qualitative descriptions. So they're just kind of comparing two things. One would be dilute and the other would be concentrated. When I talk about this term concentration, a definition for you is just the amount of solute in a given amount of solution. Okay, so again, we can have general terms like dilute and concentrated, but we can also apply math to it, which we will in just a minute. If our substance had a color associated with it, and not a lot of them do. If you'll notice in this class, a lot of our solutions look clear. They look like water, right? And so there's no way for you to tell how much is in there. And honestly, no way to tell what it is if it wasn't labeled, but definitely no way to tell how much is in there. But if it did have a color, Let's say we were working with a copper solution. Copper is blue in solution and it's really pretty, and that would allow us to tell how much there is. Or like this, let's say we were making that Kool-Aid I was talking about earlier. If we just put in a little bit of our cherry Kool-Aid packet, it would make a really light color because there's not a lot of solute in it. But as I add more and more and more of our Kool-Aid packet, it would get darker and darker and darker because I'm adding more of our solute. So it would become concentrated. So dilute is a solution that contains a relatively small amount of our solute, whereas concentrated will contain a relatively large amount of our solute. So again, it's all relative here, right? One of them would be dilute because there's not a bunch, and the other one would be concentrated because there's more, but you really have to have something to compare it to if you're saying dilute and concentrated. So here's another way of looking at it. Again, dilute, if it has a color, is always going to be lighter in color, like this one over here. And the reason is because there's not as much of those colored solute that's been dissolved in our solution. Whereas if we have a lot of our solute, like this one over here, right? If we have a lot of our solute, then it's going to be darker in color, and we will call that concentrated. So concentrated has a lot of solute, but not a lot of solvent, whereas a dilute solution would have a lot of solvent and just a little bit of solute. All right, go ahead and complete problems number 8 through 21 on the Chapter 9 lecture worksheet. Once you're done, come back and we'll get into some math. Okay, so far we've talked about qualitative expressions of concentration. Things like concentrated, which means it has a lot of solute, versus dilute, which means it doesn't have very much solute, right? But you've noticed by now that this is a math-based course, and we need to have numbers to describe how much stuff is dissolved. It's not enough to just say, oh, there's a lot, or oh, there's not very much, right? We need to know, okay, how much is there, right? Especially if it's a clear liquid. It's a little bit easier with things that have a color, right? If it's, lighter, it's dilute. If it's darker, it's concentrated. But most things really look like water. So we need to have a better way, a mathematical way, to describe how much stuff is dissolved. We're going to learn 2 different expressions of concentration today. The first one will be percent by mass, which is also called mass percent. This is our symbol. So it's percent mass over mass. Our definition here is the mass of our solute, so the mass of whatever's being dissolved, divided by the mass of our solution. This will be the total mass of both the solute and the solvent. So it's, essentially the same as percents we've done before. It's the part we're looking at divided by the total times 100. Okay, so it kind of follows our definition of percent we've already used in this class. The second type of quantitative expression will be molarity. So our unit for molarity is this capital M, and make sure it's capitalized. Okay, molarity is going to be used throughout the rest of the course, so make sure you are really solid on how to calculate the molarity of something. Also be good at mass percent, but molarity is the one that we use the most in chemistry because it allows us to do some cool conversions in train tracks, which we'll learn in a later chapter. Okay, so make sure you're really solid on molarity. Molarity is defined as the moles of the solute divided by the liters of solution. And we'll see some examples of that in just a little bit. So let's calculate mass percent. This one says calculate the mass percent of sodium chloride in a solution prepared by dissolving 50 grams of sodium chloride in 150 grams of water. Okay, as soon as you see that this is a mass percent problem, I would figure out, okay, what's my formula? So my formula was that the mass percent is the mass of the solute divided by the mass of the solution times 100. Okay, do you see that we have sodium chloride and water? We're making, salt water, essentially. But if you didn't know which one's the solute, remember the solute is always the one with the smaller amount. So when we're doing these types of problems, the solute is always the one with the smaller mass. So even if you didn't know what these things were, you should see, oh, there's only 50 grams of sodium chloride. That one's my solute because there's more of the other thing. Okay, so that's my solute. And then it has 150 grams of water. But if you see down here, this says mass of the solution. So remember, this mass is going to be the total. So to figure out the total, we take our 50 plus our 150, and that's where we're getting this mass of the solution. Okay, so the mass of the solution is always going to be the solute and the solvent added together. So it'll be our 50 grams of our solute and our 150 grams of our solvent. So together we get 200. All right, so now we can plug things in. Our mass of our solute goes on top, that's our sodium chloride. Our total mass of the entire solution goes on the bottom, and then we'll multiply that by 100 to turn it into a percent. So we get 25% of sodium chloride. So here, the substance that you're always going to put there is going to be the solute. So you're going to have a number, a unit, and a chemical, just like normal. Okay, and again, that chemical that you're having there is always the solute. Let's try this one. This says, what is the mass of sodium carbonate needed to make 350 grams of a 12.3% aqueous solution? Okay, so this is a little bit different. This one is saying, what mass of our solute do we need? Okay, so we're going to need to do a little bit of rearranging of this problem in order to solve for our answer. So let's figure out what we know. We know that we have 12.3% at mass percent, right? So when we were looking at like that on the last problem, the what does it equal? This is the what does it equal, right? It's 12.3% sodium carbonate. It also says we have 350 grams of solution. So that is our total mass. That's going to be our solute plus our solvent. All right, so we're solving for the mass of our solute. So here's our equation here. We have our mass percent is equal to the mass of the solute divided by the mass of the solution times 100. So this is what we're solving for up here. So to rearrange this, we need to divide both sides by 100 to make sure that this is gone, right? That gets rid of that. Then we are going to multiply both sides by the mass of our solution. And a solution is abbreviated SOLN. By multiplying both sides by the mass of our solution, then this is gone, okay? And that will leave us with our mass of our solute by itself. So we're getting that the mass of our solute is equal to the mass percent times the mass of our solution divided by 100. Once we've rearranged that equation, now we can go ahead and plug things in. So our mass percent was 12.3, and you'll notice I left this as a percent. Okay, so make sure to do that as well. Then you'll multiply by mass of solution and divide by 100, and that will get you your answer. So here we needed to do a little bit of rearranging before we could solve this problem. Alrighty, I want you to get some practice using the mass percent. Go ahead and complete problems number 22 to 26 on the Chapter 9 lecture worksheet. Once you're done, come back and we'll talk about molarity. Okay, so our last topic for today is calculating molarity. Like I said, this is probably our most common unit of concentration for chemistry because it deals with moles. We've already done a lot of calculations with moles in this class, and we're going to do more moving forward. So being able to convert moles of something into liters of something is going to be really, really useful. Okay, this will actually end up being used as a conversion factor in our train tracks later in the course. So it's really useful for chemists because it sets it up really nicely for mathematical calculations. Okay. So let's go ahead and try this out. This says calculate the molarity of a solution prepared by dissolving 9.35 grams of potassium chloride in enough water to prepare 250 milliliters of solution. All right, so it says we're calculating molarity. So our first thing we need to do is figure out what our formula is. Molarity here, right, molarity is a capital M, is moles of solute over liters of solution. Well, you'll notice though, we weren't given moles of our solute, we were given grams of our solute, right? But we know how to convert grams to moles. The way that we convert grams to moles is by doing a train track. We'll take our mass of our substance divided by the molar mass, right? Remember, grams of our solute has to cancel grams, and that will equal 1 mole. So just convert grams to moles, just like we've done before. Nothing fancy, same old, same old. We're just going to take our grams divided by the molar mass, get our moles. And we also, though, so that takes care of moles of our solute. We also need to have liters of our solution. They gave us milliliters of our solution. But we know how to, convert milliliters to liters. We will remember that there are 1,000 milliliters in 1 liter. So if we have 250.0 milliliters, we can say, okay, well, there are 1,000 milliliters in 1 liter. So if we divide by 1,000, essentially, that's what we're getting for our liters. So once we've converted grams into moles, and we've converted milliliters into liters, now we can use those two pieces of information to solve for molarity. Molarity is our number of moles of our solute divided by our liters of solution. All right, let's try this one. This one says how many grams of potassium hydroxide are required to prepare 600 milliliters of a 0.450 molar potassium hydroxide solution. Okay, so this one is a little bit tricky. Do you see it's asking for how many grams? Okay, so let's think about this. Our formula for molarity is moles of solute over liters of solution, but this is asking for grams of potassium hydroxide, which does not show up in this formula. So the way that this plays out is we are going to need to solve for our moles of potassium hydroxide and then use a quick train track at the end to convert moles of potassium hydroxide into grams of potassium hydroxide using the molar mass. So that's kind of our overall scheme. Okay. The first thing, though, we need to do, since we're trying to solve for moles of our solute, we need to rearrange this equation. In order to get moles of our solute by itself, we are going to multiply both sides by liters of solution. Once we multiply by liters of solution, this is gone and moles of solute is left by itself. So moles of solute is equal to molarity times liters of our solution. Once we've got that, then we can plug things in. We'll take our molarity times our liters, and that will get us our moles of potassium hydroxide. But again, this problem wasn't asking for moles. This problem was asking for grams. So once we get our moles of potassium hydroxide, we can plug that into a quick train track and use the molar mass to convert moles of potassium hydroxide into grams of potassium hydroxide. Alrighty, we have some more practice problems using molarity. Those are problems number 27 to 35 on the Chapter 9 lecture worksheet. And this is actually the end of our Part 1 of Chapter 9. We covered a lot of ground today. We talked about solutions as a whole and the factors that kind of go into making our solution, like dissolves like, right? Polar substances dissolve in polar substances, and nonpolar substances dissolve in nonpolar substances. We also looked at the ways to increase the rate at which something dissolves, right? That was heat it up, stir it up, crush it up. And those allowed us to increase the rate of solvation because they increased the rate at which those solute molecules bumped into the solvent molecules and allowed them to dissolve. We also discussed solubility limits, and we said that the maximum amount that could dissolve was called a saturated solution. Something that had less than that maximum amount was called unsaturated, and a solution that was temporarily holding more solute than it normally could would be supersaturated, which I told you was kind of a special condition. We then learned how to talk about concentrations in different ways. We used the terms dilute and concentrated to talk about solubility in kind of a qualitative manner, but when we needed to talk about concentration in a quantitative manner and applying math to it, we are going to use the calculations of mass percent and molarity and molality, which we'll get to later. But again, we did a lot of work today and we learned a lot of new things. So make sure you are really getting the practice you need with these lecture worksheet problems. As always, check your work against the answer key, but if you ever have any questions, please let me know. I'm more than happy to help you with any calculations or concepts that are tripping you up. Remember, I teach chemistry because I like to talk about chemistry. So if you have a question, I promise you're not bothering me. I really do want to help you out. Otherwise, keep working hard, and I will talk to you guys next time.